The topic of this talk is isotropic dynamic hierarchical clustering. It may sound a bit complicated, but we will explain all the terms. Generally, this belongs to the realm of big data. AT&T is definitely a major player in the big data game, and everything relevant to big data is very important. A great number of AT&T mobile and TVOS customers produce lots of data. The methods of machine learning and clustering are developed to extract valuable information from piles of raw data. On the other hand, we should not expect a miracle. Possession of huge amount of data doesn't necessarily guarantee that there is any valuable information. For example, for process of gold recovery to be successful, it is required that the material should be rich of gold. Big data is a relatively new field, so it is dynamic and flexible. Some techniques applied to big data and machine learning were originally developed in our fields, such as applied factor analysis or operations research. In this presentation, we will show that a now well-known concept can be successfully applied to clustering. From the course of computer science, we know that storing, sorting, and searching are usually not efficient on streams and linear lists. Better result can be achieved when the data form a hierarchical structure. There are a number of slightly different trees: a binary tree, a search tree, and black and red tree, and finally our favorite B-tree. This picture illustrates a B-tree in one-dimensional case. A B-tree possesses a number of valuable properties. The B-tree is balanced, that ensures logarithmic time efficiency. The B-tree is populated, there are no empty or overloaded nodes. The tree balances itself, then a new element is added to the tree. It would be great if we could apply a B-tree to storing and processing big data. Our goal is clear. We would like to apply a B-tree to get a hierarchical clustering. This approach is well scalable. We do not need to put any assumption on the amount of data. If there are few data items, the B-tree is small. If we have lots of data, the tree will get huge. But in any case, the tree is well structured. It will show how many levels are needed to cluster the given data. There is no need to define top-level clusters a priori. We also add essential mathematics to our implementation. As stated above, hierarchical clustering means that we may process the data on a level of subtrees. For each subtree, we calculate the number of elements as well as other statistic values. The good thing is that we don't need to recalculate all these values each time a new element is added to the tree. We can update statistical values in an incremental way. The number of elements need to be increased by 1, the mean should be moved towards the new element by 1/10 of the distance, and the great thing is that the standard deviation can be updated in the similar way. The approach explained above allows us to provide functionality for manipulating aggregated data. For example, a subtree can be efficiently added or removed from the tree without complete recalculation of statistical values. Why it hasn't been done before? Actually, it's rather challenging to extend a B-tree to a multidimensional case. The easiest way would be to combine multidimensional indexes into one index and to create a B-tree based on that index. Unfortunately, the indexes cannot be combined in a symmetrical way. One index will dominate other indexes. A better approach is to consider data item as points in multidimensional space and to divide the data into subtrees by rectangles. This technique is called R-tree. The indexes are symmetrical, but the directions in space are not isotropic and depend on the given basis. What we aim for is truly isotropic clustering in a Euclidean space. At each level, the subnodes should look like multidimensional soap bubbles. The subnodes are limited with the multidimensional hyperspheres. Each node has a center, and each subtree contains all the elements which are located closer to its center than to the centers of our nodes. So the limited spheres are cut, and the whole structure is very similar to the picture shown on this slide. Now let's add a hierarchy to the previous slide. It's difficult to illustrate how it works in a 1000-dimensional or even in a 3-dimensional space. So we created an illustration for a 2-dimensional space. It proves that we don't impose any rectangles. As for our project, it was used for a troubleshoot help system which operates in 1000-dimensional semantic space. Please contact me with any questions about the parsing the documents and mapping them to the points in the semantical space. Our project is implemented as a library of Java classes. The library follows object-oriented design. The B-tree, nodes, and data elements are implemented as classes with convenient interface. The database level of the project is completely separated from the middle tier. The nodes and data elements correspond to the beans, which are stored in MySQL or Oracle database. The database provides read-write storage procedures, which are automatically wrapped into Java classes. The library interface supports adding new elements to the B-tree, searching for closest leaf element, or the closest internal node. The node provides statistic values of subtrees, such as the number of elements, the mean, and the standard deviation. The project was implemented to the level of a working example. All in all, I would say that the message of this presentation and of the project in question is that today big data science is still an open field. The situation will probably change in a few years. Everything will be known, solid, and fixed. But right now, we enjoy the luxury to create pilot projects and to compete successfully with the currently available technologies. That's all. Thank you for your kind attention.